5.2 is in the binomial probability distributions. And in order for us to have a binomial probability distribution, we need to have 4 requirements. This being the procedure has a fixed number of trials or observations, and the number of trials is denoted with a lowercase n. The trials are independent, where the outcome of any individual trial does not affect the probabilities in the other trials. Just like what we looked at before when it comes to independence involving the probability of 2 events occurring at the same time. Each trial must have all outcomes classified into 2 categories, success and failure. Success will be denoted by a P and failure by Q. You can also think of failure as just 1 minus P. And the probability of success remains the same in all trials. So, with S and F being success and failure, we have these notations. So probability of success is equal to P. Probability of F is equal to 1 minus P, or Q for the probability of failure. N is the number of fixed trials. X is the specific number of successes in N trials. So X can be any whole number between 0 and N inclusive. P is the probability of success in one of the N trials. Q is the probability of failure in one of the N trials. And P of X is the probability of getting exactly X successes among the N trials. So, the number of successes then is our X, in this case, for the binomial probability distribution, once we have these 4 requirements, of course. So, for example, when Gregor Mendel conducted his famous hybridization experiments, he used peas with green pods and peas with yellow pods. Because green is dominant and yellow is recessive, when crossing 2 parents with the green and yellow pair of genes, we expect that 3/4 of the offspring peas should have green pods. That is, the probability of a green pod is 3/4. Assuming that all parents have the green-yellow combination of genes, we want to find the probability that exactly 3 of the 5 offspring peas have green pods. And before doing said calculation, we first need to check. Does this procedure result in a binomial distribution? So for this, we first need to verify that we have a number of fixed trials. So for this, we are told 3 of those 5 offspring peas have green pods. We have 5 offspring peas, so yes, the number of trials is fixed. So number of trials is fixed. The second one is that these need to be independent. Well, based upon those offspring peas and the pods that they produce, if one produces a green pod, the next one producing a green or yellow pod should make absolutely no difference. So yes, these trials are independent. Trials are independent. For the third part, we want success and failure to be defined events for this. So when we have a success, that just refers to having a green pod. Likewise, failure this is the yellow pod. For the fourth one, we need to have a fixed probability of success. In this case, that'll be that 3/4. So P will be 3/4, or written as a decimal, 0.75. And then if this procedure does result in a binomial distribution, identify the values of n, x, p, and q. So n, we were told there were a total of 5 trials. X, we were told we want 3 successes. P, we stated that the probability of success is 0.75. And Q will be 1 minus 0.75. So the probability of failure will be 0.25 in this particular binomial experiment. Now, when we sample without replacement, which would typically result in dependent events, but we can apply the 5% guidance for this. When sampling without replacement and the sample size is no more than 5% of the population size, we would treat the selections as being independent, despite the fact that they're technically dependent events. And now, to calculate binomial probabilities, one of the ways to do so is with the formula. The probability of exactly the number of successes, x number of successes, is n factorial divided by n minus x factorial times x factorial times p to the x power times q to the n minus x power, for x being 0, 1, 2, all the way up to n. And this formula, if you recall, this is n choose x, or also written as n and x, kind of in these parentheses, just to mean that n choose x. N to the number of trials, x the number of successes, p probability of success, and q probability of failure. The second way is to use technology, and the way we've been doing that inside this class is to use SAS. So the overall structure of that SAS code would be data, some name. I just like to call it binomial, since that's the whole point of the actual exercise. X would be equal to PDF of, then binomial in quotation marks, x, p, and then n, and then run. Alright, and you could look at my corresponding SAS tutorial video once that is released as well for that. And then table A1 and appendix A in the back of the textbook could also be used, but that's also not the preferred method, since, as you can imagine, the tables are huge for these. So for example number 2 here, assuming that the probability of a p having a green pie is 0.75, as in example 1, calculate the probability of getting exactly 3 p's with green pods with 5 offspring p's are generated. So writing out that formula, this will be probability of getting 3 successes. This will be 5 factorial divided by 5 minus 3 factorial times 3 factorial times 0.75 to the third power times 0.25 to the second power. And if we toss this into a calculator, use SAS or whatnot, we will get a value of 0.264. And the calculation step for this in SAS would be x is equal to PDF of this would be binomial in quotations. X was 3, P was 0.75, and N was 5. And the interpretation of this would be the probability of having exactly 3 peas with green pods according to this binomial experiment among 5 offspring peas is, as we calculated, 0.264. Assuming that boys and girls are equally likely, we must find the probability of getting exactly 5 boys in 8 randomly selected births. So probability of x is equal to 5. This would be 8 factorial divided by 8 minus 5 factorial times 5 factorial times 0.5 to the 5th power times 0.5 to the 3rd power. Tossing this into a calculator, or SAS, will give us a value of 0.219. When it comes to a binomial distribution, our parameters, since the binomial distribution is a special type of discrete probability distribution, the mean, we could rewrite the formula a little bit. The mean, mu, for this is going to be the number of trials times the probability of success. So n times p. The variance, sigma squared, is just n times p times q. And the standard deviation is the square root of n times p times q. We could also use that range rule of thumb. So significantly low values are less than or equal to mu minus 2 sigma. Significantly high values are greater than or equal to mu plus 2 sigma. And values not significant are between mu minus 2 sigma and mu plus 2 sigma. So, for example, find the mean and standard deviation for the number of peas with green pods when groups of 5 offspring peas are generated. We want to assume that there is a 0.75 probability that an offspring pea has a green pod, just like a lot of these examples have been. So for this, we are using an n of 5. Probability of success of 0.75. Probability of failure is 0.25. So the mean of this random variable is going to be n times p. So 5 times 0.75. So the mean of this would be 3.8. For the standard deviation of this, the square root of n times p times q. So square root of 5 times 0.75 times 0.25. We would toss that into a calculator and get an answer of about 1.0. Significantly high values from the range rule of thumb again. This is the vast majority of values should lie within 2 standard deviations of the mean. A value is significant if it is at least 2 standard deviations away from the mean. So significantly low values are mu minus 2 sigma or lower. Significantly high values are mu plus 2 sigma or higher. And the values not significant are between mu minus 2 sigma and mu plus 2 sigma. And for my next example, in an actual experiment, Mendel generated 580 offspring peas. He claimed that 75%, or 435 of them, would have green pods. The actual experiment resulted in 428 peas with green pods. Assuming that groups of 580 offspring peas are generated, find the mean and standard deviation for the number of peas with green pods. So, before doing these calculations out, we know n was 580, p was 0.75, and q was 0.25. So the mean of a random variable is going to be 580 times 0.75. Toss that into a calculator, you get 435.0. The standard deviation takes the square root of n times p times q. So square root of 580 times 0.75 times 0.25. Tossing that into a calculator gives an answer of about 10.4. For the range rule of thumb to find the numbers of peas with green pods that separate significantly low values and significantly high values from values that are not significant. Then based on those numbers, can we conclude that Mendel's actual result of 428 peas with green pods is significantly low or significantly high? And then does this suggest that Mendel's value of 75% is wrong? So for the significantly low, we need to take the mean minus 2 sigma. So 435 minus 2 times 10.4. That should be 414.2. So significantly low values are less than or equal to 414.2. And the significantly high values, I mean plus 2 sigma, so 435 plus 2 times 10.4. Tossing that into a calculator, we got 455.8. So significantly high values are 455.8 or higher. And now this 428 is between these two. So 428 can occur by chance. Can occur by chance. This also means that 75% is not wrong. So the claimed 75% is not wrong. For the probabilities of significant results, we've seen these previously, but significantly high number of successes occurs when the probability of X or more successes in n trials is 0.05 or less. So probability of X greater than or equal to X is less than or equal to 0.05. Significantly low number of successes is if the probability of X or less successes in n trials is 0.05 or less. So probability of X less than or equal to X is less than or equal to 0.05. Thank you.